In the previous module, we learned that the total amount of energy in a system remains conserved, or in other words, you can neither create energy nor destroy energy. And in short, this thing or this statement is called the law of conservation of energy. So it means that energy should always remain conserved. You can neither create energy, and you can nor can you destroy energy. So this particular chapter is basically focused on two energies which we've covered. Firstly, kinetic energy. So if we talk about kinetic energy, Ke, and it also focuses on potential energy, Pe. These two things together are called mechanical energy. Let's just call that Me. It's mechanical energy, and it is just composed of these, it includes these two types of energies, and if we add them, we get the total mechanical energy of a system. So for example, if some ball is at some height and is also moving, it has some kinetic energy and also has some potential energy. Or if we combine the two, we may say it has some mechanical energy, which would simply be the sum of kinetic and potential energy. And if we have to in some isolated system where we have no other, and if we are not talking about some other forms of energy like chemical or light energy, if we are only focusing on these two types of energies, and we have some isolated system which is not interacting with the rest of the world, so the sum of these two should remain conserved for now. We won't get into other forms of energy, but basically you can restrict the conservation of energy to these two energies for this chapter. And so these two should remain, well, some constant value. So if the sum of them is, let's say, 2 joules, so it should always remain 2 joules if the system is isolated. And we can also say that, so kinetic energy is given by, well, half mv square, right? mv square by 2, or half mv square, plus potential energy is given by mgh, and this should always remain constant. So that is simply the conservation of energy for a purely mechanical system, or a system in which we have only kinetic and potential energies under consideration, and the system is isolated. Now, one thing that needs to be noted here is that, for example, if I have two objects, maybe I have these two markers here, this marker, and I'll just take this marker. For example, if this one is stationary and the other marker comes rolling and hits it, right, and it transfers its momentum into this. So in such a system, so we've learned that momentum is always conserved in every collision or in every process. Similarly, kinetic, or rather mechanical energy, is also conserved in most collisions, but the catch here is that when these two hit, so there is no other place that momentum can go, right? Either momentum can be in this object or in that object, so it must always be conserved. So the momentum of this before the collision should be equal to the momentum of the system after the collision. But while they collide, you hear that? See, they produce some sound. So that sound is also energy. So obviously you cannot create energy from somewhere, so that sound has to come from somewhere. So to compensate for this sound loss, some kinetic or potential energy has to reduce. So yeah, in real life cases, the total mechanical energy is not conserved, because in most collisions we have sound energy, and if the two hit at a very high velocity, we may also get some sparks, which is heat or light energy, or maybe combination of both. So yeah, so in real life cases this might not be always true, because you might have some energy that is being wasted as sound or other forms of energy, but in ideal situations this is true, or in situations where we only have pure mechanical energy and no other energy is being involved. But yeah, conservation of momentum is a universal law, and that should always be true, and it has no other exceptions. So that is one point. The second point I'd like to raise in this video is that, so we just right now saw that so even in the last video where I had given you the demonstration of a ball going high up in the last module, so So even in that module, we had seen that initially the football had some kinetic energy, but as it went higher up, that kinetic energy got converted into potential energy. And so that clearly shows us that energy is interconvertible. So energy can be converted from one form to another. If some object has kinetic energy, that energy may get converted into potential energy. And that is only one example, but in other examples we may have other forms of energy that are being interconverted. For example, your tube light. So your tube light is powered by electric power, right? It is powered by electricity, electrical energy, and the tube light converts that electrical energy into, well, light energy, right? Like we can see light all around us. So a tube light is a device that converts electrical energy into light energy. And similarly, you may look around and you can spot so many places where energy is being converted from one form to other. And it could be from chemical energy to heat energy, and there are so many examples all around us. And for a moment, if you want to appreciate the beauty of this fact, just imagine a world where interconversion of energy is not possible. Well, in that kind of a world, life or even any other process is almost impossible, because the basis of life is interconversion of energy, right? Or basis of a lot of processes, interconversion of energy. How do we work? We work by deriving energy from food. So food has chemical energy in it, and we use that chemical energy to do work. So we may move, which is kinetic energy. We may climb a mountain, and we may gain potential energy. But all that energy comes from the chemical energy from food. Also, we may have so where does the food gain its energy from? The food gains its energy from, well, sunlight, which is light energy, right? So it is this interconvertibility of energy that makes life possible, and also many other processes. It makes other processes also possible. So yeah, those were the 2 points that I wanted to raise in this video. That's it for this video.